So now it's my very great pleasure to introduce Steve Butler from Iowa State University for today's talk. I'm going to shamelessly read off his website because he has a lot of math interests. They are spectral graph theory, enumerative combinatorics, mathematics of juggling, discrete geometry, and generally mathematics of fun things. So this is bound to be a fun talk. But in particular, today he'll tell us about a short course in spectral graph theory. So thank you, Steve.
All right, well, thank you. Wow, what an introduction. And I got to know Esther way back when. She did an RU with me, so it's nice to see her doing so well. So this will be, like I say, a short course, kind of a crash course. So we're not going to necessarily go into a lot of depth because spectral graph theory has really grown in the last couple of years, and it's a beautiful topic. But I hope I will convince you that there are some interesting things going on. Now, you might find yourself becoming distracted or sort of losing interest. Maybe, I hope not. But if you do, here's a pleasant distraction for you. So here's a small set, has 3 numbers in it, 2, -1, -1. So it's a multi-set. And you can see I've written here the addition table and the multiplication table. Not too hard since there's only 3 numbers. But here's the interesting part. You'll notice that they both have a single 4, they both have 4 1s, they both have 4 -2s. In other words, the s plus s, all possible sums, and s times s, all possible products, are the same, including multiplicity. Now, you might say, okay, can other things do this? Well, sure. All zeros, easy. All 2s, easy. Anything else? And that's the challenge. So if you find yourself needing something to work on, just think about, all right, what are some other sets which have this property? And the other thing you might think about, what does any of that have to do with spectral graph theory? Why is he bringing this up in this talk? Well, wait till the end, you'll see. All right, so where to begin? Well, not surprisingly, if we're going to talk about spectral graph theory, it all starts with graphs. So we have a graph, and if you hear the word graph, oftentimes what pops into your mind is a picture where you have these points, which are the vertices, these edges, which are the connections. Now, of course, that's not what a graph is. A graph is, sets of vertices and edges with certain relationships. But we like to think of graphs in this way. But how do we store a graph? Like, what's the important information? So one way that we can do it is as an array. And in particular, we can index the rows and the columns by the vertices. We say, okay, any particular entry tells us the relationship between those pairs of vertices. Great, wonderful. Now we've stored our graph. Well, along come some spectral people working linear algebra and say, look, don't call this an array. No. Call it a matrix. And we're like, okay, all right. Array, matrix, potato, all right. But it turns out that matrix is an array with benefits. So in other words, we actually gain something by switching from just saying, oh, there's this square table of numbers, and say, no, think of it as a matrix. And in particular, when we think of matrices, there's these wonderful properties that come into play. Well, that's actually doesn't go in both directions, because matrices represent linear transforms, and you get eigenvalues. And so these are where the word spectral comes into play. The graph is a matrix. You have a matrix, you got eigenvalues. Wonderful, wonderful. Now, here's the challenge. Sure, if I have the graph, I can get the eigenvalues, but what about this direction? And in other words, if I know the eigenvalues, how much do I know? And this arrow, this is really the core of spectral graph theory. In other words, saying, all right, I know something about the eigenvalues. What can I conclude about the structure of the graph? And what do I learn? What don't I learn? What are some things I can't understand? Now, in all fairness, a little bit of spectral graph theory is in this other arrow as well, but that is where we want to talk about. All right, well, great. But now there's a question. See, I said we can think about a graph, we can associate it with a matrix, but which matrix? And turns out, well, there's not one answer, there's many possible answers. So we need to go visit the Build a Matrix workshop. So how does one build a matrix? Well, the key idea is to think about what's the matrix representing. The matrix says I'm storing this information in a nice table and indexed by vertices. So I say, okay, well, look, each entry is some relationship. I have two vertices, u and v, and I want to ask the question, okay, how am I related? Now, there's lots of ways we could answer this question, which means that there's lots of different matrices which show up in spectral graph theory. Now, the three common ones, and I don't want to say these are the only ones, but there's three common ones are, well, we can look at the adjacency. Now, the adjacency says, look, am I connected or am I not connected? All right, that's pretty easy. And that leads to what we call the adjacency matrix, which is probably one of the most studied matrices. It's probably the most obvious matrix, so that's a good reason why it's one of the most studied. There's other ones. There's something called the Laplacian, and there's a signless version. And we'll see that the Laplacian involves some negative signs. So the signless Laplacian is sort of the optimistic version of the Laplacian. So it's like, I don't like negatives. I want everybody to be positive. So, okay, so there's adjacency. Another possibility is to look at transition. So in other words, I can say, how likely am I to move from one vertex to another? That's the question when I'm asking about transition. And so this comes into play for things like random walks and a personal favorite, the normalized Laplacian. And the third is the distance. It says, okay, I have a graph and I have two vertices. How far apart are these two vertices? And that can define our entry. Each one of these leads to a different matrix. Different matrices have different properties. And so we'll go through and take a look at some of these. So we'll start with the adjacency matrix. And like I said, it's probably one of the most obvious matrices when you're starting because it's recording our adjacency. So it's going to be 0 or 1. 1 if a pair of vertices is adjacent, 0 if we're not adjacent. So here's a graph, the PAW graph. Very simple graph. And I've indexed the vertices 1, 2, 3, 4. And here would be the corresponding adjacency matrix. So there's our matrix. And of course, when we talk about spectral graph theory, we say, all right, well, look at the eigenvalues associated with that. Now, I should pause for a second and make a comment that one of the nice things about the spectral part of looking at these matrices is that we kind of lose information about how we labeled things. So in other words, it doesn't matter how we label the vertices. Ultimately, the eigenvalues are still the same. We permute the matrix, yes, but the eigenvalues don't change. And this is one of the reasons why we like spectral graph theory, because it's saying, look, we're kind of going to lose information about the labeling, but that's probably a good thing because sometimes labeling can be misleading or, well, very suggestive. So, okay, great. You might notice there are some graphs down here. You'll keep seeing some graphs pop up as we go from matrix to matrix. And these graphs are interesting. Why? Well, you have C4 with a single isolated vertex, and here's the star, K14. And they're interesting because they are two graphs which are not the same. Easy to prove that these are not the same graph, but they have the same spectrum for the adjacency matrix. Now, way back long ago, there was the hope. It's like, okay, maybe if we have the eigenvalues, we have everything that we could possibly want to know about the graph. And then after about 2 minutes, someone said, well, what about this pair? Ah, darn it. Okay, well, we'll have to do some work. And so co-spectral pairs, actually, it's a very interesting topic because it reveals the weaknesses of a matrix, and each common matrix does have weaknesses, things that it cannot detect. Now, we call this the adjacency matrix, but there's another way to think about what the adjacency matrix is capturing. So that comes in from the following fact. So if I take this adjacency matrix and I raise it to the kth power, and I look at any particular entry, well, it's counting something. It's a number. And the thing that it's counting is the number of walks of length k that start at vertex I and end at vertex j. So in particular, this is a wonderful tool for walk counting. So if I want to go out and start counting walks, perfect. I know how to do it. And since we know how to count walks, we can say, well, are there any interesting walk lengths? Well, it turns out there's some very interesting walk lengths for low numbers. And for example, how about walks of length 2? All right, well, there's only a couple of things you can do. You can go and sort of move to a vertex, move to another vertex, or you can go back and forth. So you'll notice that when I look at walks of length 2 that return to the same vertex, well, that's really going to be the edges times 2. Now, because you can really start at either vertex and go back and forth. But I can also say, hey, that says, look at a square, walks of length 2, look on the diagonal. That's all the walks of length 2 that return to itself. So we come up with the beautiful fact, the trace of a squared is twice the number of edges. But we also know from basic linear algebra, if I have the trace of a squared, it's the sum of the square of the eigenvalues. Very similar argument. You can say, hey, the trace of a cubed, well, if I want to look at walks of length 3 that start and stop at the same point, the only way I can do it is move along a triangle. But of course, I can pick vertices. Which vertex do I start at? Which way do I traverse? So we end up with 6 times the number of triangles is the sum of the cube of the eigenvalues. And so there are some really, really nice results. Now, I will say that we should think of these as actual linear operators. So in other words, when I think of the adjacency matrix, it's a linear operator. It's doing something to the graph. And sort of what we should think of happening is if I want to talk about, ax equals y, well, the way I like to think about this is this vector x. I like to call this a valuation. Now, what does that mean? Well, it's a valuation on the vertices. I'm going to assign each vertex a specific value. All right, maybe I say this vertex has weight 2, this one has 3, that has -1, whatever it is. And now, what happens? Well, this ax says, look, do something to your assignments. And we're going to produce a new assignment. And in particular, the new rule says, look, if I have a vertex here, let's say here's x1, and I look at some neighbors, x2, x4, x6, well, what's going to happen is that when I come into my new valuation, my new assignment, it says, look, according to the adjacency operator, it says add up the neighbors. So that would be x2 plus x4 plus x6. So there is actually representation. The graph is having information about what happens to it when you apply the adjacency matrix. So there's some interesting stuff going on. Now, one of the nice things that we can talk about with the adjacency matrix is something called discrepancy. So what is that? Well, discrepancy for a d-regular graph is a parameter. It's the smallest number, alpha, so that for any subsets x, y, your vertices, so think of the picture as this. You have your vertex set, are really just the whole graph, and then you have x and you have y. So here are our subsets. So what we want is we want to look at a couple of things. So the edges between x and y is asking what's going on here. So how many edges go between? This is the actual number of edges. All right, great. And then we subtract d over n, size of x, size of y. Well, what's that? Well, this would be if we had everything placed randomly. So this is the expected number of edges under some sort of randomness. And now what we're looking at is discrepancy says, hey, let's compare these two. Let's look at the actual versus the expected. And let's see how small it can get. So what we have is this parameter. This is sort of a normalizing factor that we have to take into account just to make sure we don't get thrown off by strange small sets and so forth. So in essence, this parameter alpha, which is our discrepancy, is really saying how random are we? In other words, how random-like are we? So if we have a small value for alpha, well, that's great. It says that most of the time when you look between sets, it seems like the edges are there fairly randomly. Whereas if alpha is fairly large, well, that says, okay, there's some sets out there where the edges between them are very non-random. All right, great. Well, what does this have to do with the adjacency matrix? And the answer is the expander mixing lemma. This is a result due to Noga Fan Chung. It says, look, this parameter, this alpha, is bounded by the second largest singular value of the adjacency matrix. All right, good. So somehow the adjacency matrix is going to tell us, hey, how random are our edges? Now, how does the proof go? You might notice I skipped over something. There's this linear algebra result. Well, of course, spectral graph theory is all about looking at matrices. And so it's not surprising that we should see linear algebra coming in. And the linear algebra result says, if you look at, for any matrix B, you look at x star by, it's always bounded by the largest singular value of the matrix B times the size of x, size of y. These are the two norms. All right, well, great. What does this have to do with discrepancy? And the answer is a very simple proof. And of course, every math talk should have at least one proof, right? That's the goal. All right, so what's the proof? Well, you're going to let your vector x be what we call an indicator function. So it's going to be 1 wherever I have a vertex in x and a 0 otherwise. Because remember, we're talking about these vectors are assignments. And so these kinds of vectors are very important in spectral graph theory, saying, hey, let's look at essentially subsets. So when you're looking at problems involving subsets in some ways, you can oftentimes tie it into spectral graph theory. The vector y, well, similar thing, it's the indicator for the set y. And now for your matrix B, you take the adjacency matrix minus d over n times j. And then you apply this, and life is good. Now, okay, I'm going to skip a few steps in this proof, as you can tell. But what's happening here, and why does this work? Well, the key here is there's a really important assumption that we made. This assumption here, we're d-regular. Now that's important. And why is that important? Well, what that tells us is if you know your graph is regular for the adjacency matrix, you say that there's a really, really special vector, and it's called the all ones vector. And so this one, you should put a little halo around it. This is the most important vector in spectral graph theory. And it says, okay, everything is 1. And so not only do we know that that's a vector, it's associated with the eigenvalue of d. So what happens is that when you take A, subtract this quantity, what you're really doing is you're taking that projection onto your eigenvalue of d, and you say, okay, change it to a projection onto 0. That's what it does, is it knocks that down. And so now you run through the computation. When you take x star by, well, when I take x star ay, that's the number of edges. X star d over nj times y, that's this expected number. And then say, look, it's the second largest singular value of this matrix, but we took out the largest one, set it to 0, so it becomes the second largest. So, all right, there we go. There we go.
Hey, Steve, can I just confirm the x star is like transpose?
Yes, x star is transpose.
Thank you.
I should say what that is. You're right. Okay, we'll come back and visit discrepancy a little later. It's a wonderful topic. So our next matrix will be the Laplacian matrix. Okay, great. Well, what is it? So same graph, and here's the matrix. The rule is on the diagonal, put in the degrees. And on the off diagonal, it's similar to what we had before, whether we're adjacent or non-adjacent, except now adjacents are negative ones instead of positive ones. All right, great. Now, you might say, why are we calling this the Laplacian? Well, good question. And so sometimes we think of the Laplacian in terms of differential equations. You have this the Laplacian there. And it turns out that this matrix is actually mimicking the discrete version of the Laplace operator. So that's why we call it the Laplacian. As I mentioned before, you lose something. And here we have a pair of graphs which are co-spectral for the Laplacian matrix. And they're very different. Well, you might wonder, are they that different? Well, notice this left one has a triangle. Okay. And this right one, no triangle. And so, okay, that's the difference. So they're not the same graph. And in particular, the Laplacian can't tell if a graph is bipartite or not. Now, there's a couple of nice facts you get with the Laplacian matrix. You can certainly say, for instance, that the Laplacian is positive semi-definite. There's lots of ways to prove that. One way is if you look at this expression, this quadratic form, x transpose or x star, Lx. Okay, that's the sum over all the edges of xi minus xj squared. Well, that's always greater than or equal to 0 because you're adding up a bunch of squares, and therefore all the eigenvalues have to be positive. Well, I should say non-negative, right? Positive semi-definite. The multiplicity of 0 is the number of connected components. And so in some sense, you can use the Laplacian to say, hey, how connected am I? But of course, probably one of the most famous results is Kirchhoff's matrix tree theorem. It says the following. Well, suppose our eigenvalues, we know the first one is 0. All right, and it's 0 is lambda 0, less than or equal to lambda 1, so forth and so on, are the eigenvalues of our Laplacian. Then the number of spanning trees for the graph is 1 over n, lambda 1, up to lambda and minus 1. So in other words, you throw out that first eigenvalue, which you know is 0, multiply the rest of them together, divide by n, there you go. That's the number of spanning trees. So for instance, up here, for this graph, it's not so hard to check that the number of spanning trees, well, it's going to be 3, because there's 3 possible spanning trees. It looks something like that. And, well, can you do anything with this? There's a nice result that you can do, which is if you look at the graph, g equals kn, what happens? Well, for that, the Laplacian, it's pretty nice. It's n minus 1 on the diagonals and minus 1s in the off diagonals. So it's a very simple matrix. All right, great. Now, what's your spectrum? Well, you have 0 as an eigenvalue, and then the rest of them are n. So there's our spectrum of our Laplacian. And now, according to this, we apply the rule, it's going to be 1 over n times our remaining eigenvalues, and there's n minus 1 of those, giving us to the number of spanning trees of the complete graph, n to the power n minus 2. Well, that's a nice result. That's Cayley's formula for the number of labeled trees and n vertices. So that comes out. So there we go. All right, well, switching gears on to more matrices, right? Well, our next one will be the probability transition matrix. So this is one that's connected to random walks. And our question is, okay, how likely are we to move from one vertex to another vertex? So for instance, if I'm at vertex 1, I'm very likely to move to vertex 2. I really don't have a choice. I'm just kind of only one way out. On the other hand, if I'm at vertex 2, I really have equally likely chance to end up in any of the vertexes, 1 out of 3. And in general, we say, look, the entry for this matrix, P, ij, it's 1 over the degree of I, if I is adjacent to j, and 0 else. So 1 over the degree, it says, okay, look, I'm going to treat each one of my neighbors as equally likely to transition to. Now you can change this a little bit and say, well, maybe I'm biased to some neighbor or another, but for now we're just going to be simple. Say, all right, let's just move to each with equal probability. And here's, again, another pair. Here we have 2 complete bipartite graphs, and they have the exact same spectrum. So we've lost information, but that's okay. We're gaining some. We're really starting to understand what's happening with this process, because this is about random walks. What's happening to our random walks? Now, one of the nice things about this matrix, which is not so obvious when you see it, is that all the eigenvalues are real. The reason I say it's not so obvious is it's not symmetrical. So when we looked at the adjacency of the Laplacian, we said, hey, things are symmetrical, which means something real is going on here. But for this matrix, well, we don't have that, but still it turns out all the eigenvalues are real. One is always an eigenvalue. And if you make an assumption, namely you have connected and not bipartite, then all the other eigenvalues have size smaller than 1. Now, connected and not bipartite is just a really sort of fun way of saying ergodic. And another way to say that is you can mix really well. So whenever we talk about ergodic things, it's like, oh, this has the potential to mix. Now, I use the phrase really well. Well, how do we know how well things mix? And the question comes down to, well, what's happening with the other eigenvalues? Because what happens with random walks? Well, what you can think of happening is you have some sort of initial probability distribution. So this is an assignment to the vertices. How likely am I at any single vertex at the start? We want all the numbers to be greater than or equal to 0 and sum to 1. So that's a probability distribution. And then we say, okay, well, how are we looking after one step? And how likely are we to be at any vertex after one step? Well, that can be answered by this taking probability distribution matrix times p. After 2 steps, take it times p squared. After k steps, take it times p to the k. And in general, as long as we mix well, what happens is this goes to something called the stationary distribution. And in the stationary distribution, you say, look, if I apply sort of one step in my process, I don't change how likely I am to be in any particular place. Now, one of the nice things that we'd want to know is, well, how quickly can we converge to that stationary distribution? And that comes back to our eigenvalues. Because if our eigenvalues are, say, small in size, near 0, then that says that when I look at this process, it's going to converge exponentially and very quickly. But if I have an eigenvalue near 1, 0.9999, yeah, it converges exponentially, but boy, 0.999, it takes a while to get small. And so understanding what the eigenvalues are can help us understand, all right, how quickly is this thing going to converge? So random walks, a lot of things about random walks can be understood through this probability transition matrix. One of the fun things I look at in recent times was Chemnitz constant. And so Chemnitz constant says, hey, how long will it take for you to get to a random vertex? Well, it turns out you can understand it through use of the eigenvalues. All right, well, closely related to the probability transition matrix, in some sense, almost the same matrix, though it doesn't look like it, is the normalized Laplacian matrix. There's a joke I heard once, and I like it, and namely that the normalized Laplacian should also be called the San Diego Laplacian, because most of the people who work with this matrix have ties to UC San Diego, where Fan Chung, who popularized it, worked, and a lot of good students. And well, what is it? You'll notice, at first glance, it's very daunting, because all of a sudden we have square roots involved. So the key is 1 on the diagonals, and then -1 over the square root to the degree of I, degree of j. And if you're adjacent, and 0 otherwise. So the square roots can throw you off, and sort of what happens, you're like, these look terrible. Why would you do that to yourself? Well, the answer is why we would do it to ourselves is it's the symmetric form of the probability transition matrix, then slightly shifted. So you notice it's the same pair of graphs. Well, that's, again, because essentially it's the same matrix, just expressed in a slightly different way. And there's ways to get around the square root. So what can we do? Well, here's a very nice application. So the Cheeger constant, what is that? Well, there's a technical definition, but what it's trying to capture here's sort of the spirit of the definition. So it's to say, I'm after a good cut. So when we're looking for the Cheeger constant, it's a measurement of how well can you cut your graph. Now, how do you know if you have a good cut? Well, essentially what you're hoping for is a bottleneck. So where you have some fairly large pieces of your graph where you can slice. So this is a good cut, where we've taken our graph into two large parts, very small number of edges had to be involved. So that's, the top says, hey, I want a small number of edges down there, but in the meantime, I want to make sure that my pieces of my individual parts are large. And so you can, of course, cut a graph into two parts very simply, just, oh, find a vertex and then cut all the edges around there. Well, that's kind of lousy because one of your pieces is super small. And the goal is to say, well, I want large pieces. So one of the things Fan Chung was able to show that says, hey, suppose you have the eigenvalues, and this is for the normalized Laplacian, then what you can see is that that Cheeger constant is tied to this eigenvalue lambda 1. So this eigenvalue here is, it's capturing, information about how easy it is to find a good cut. So if lambda 1 is small, that says, hey, somewhere out there, there's a way to cut your graph. On the other hand, if somewhere out there there's a way to cut your graph, lambda 1 has to be small. So lo and behold, you say, oh, okay, so this first eigenvalue gives us a lot of information about connectivity. And it also, of course, connects back to why the probability transition matrix. It gives you information about graph processes, random walks, and so forth and so on. I should also add that for the Laplacian matrix, you also will see the same thing, where that first eigenvalue lambda 1, that actually has some information about what's happening with your graph. And so we can learn a lot about how connected our graph is to understanding our spectrum. Okay, now one question that often gets asked with the normalized Laplacian is, all this normalizing good for us? We have all these square roots. Do we gain anything? Is there something that we can get from it? And my answer is yes, normalizing is good. And so to motivate this, I want to sort of give an example. So imagine we look at the graph, that's the internet. It's a very important graph. A lot of people spend their time exploring that graph. And so we'll simplify things. All right, we'll assume things go in both directions. And I've picked two websites. And one of them is www.funnycatpics.com. And you know it's funny because they spelled the pics with an X. It's a real website. You can look it up. They have a funny cat of the day. There's another website called google.com. That's also, you can look that one up as well. Now, if you're just thinking, oh, the important thing in my life is vertices, 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 then both of these are one vertex in the internet. So they're both equally important. But we know that's not true. I mean, one of these two websites is a major driver of internet traffic, and the other one is a search engine. So we can see that there's definitely some sort of like, wait, we're not looking at things the right way if we say, let's live in a vertex-centered world. So what do we need to do? Well, we need to change our view. And that's what the normalizing does, is it says, hey, don't become vertex-centered. In other words, when I'm talking about vertex-centered, that says it's the number of vertices. No, become edge-centered. And that says, look, the important thing is not how many things you have, in other words, how many vertices in your set, but how many connections you have. And so we call that the volume. So the volume is your number of connections, or really it's the number of edges. So that's what's being measured. And now we can go back to the expander mixing lemma that we talked about before. Remember, it used to say, okay, you got to assume your graph is regular. And now we say, no. This is all graphs, this is true. And it says the following. If I look at the number of edges, this is the actual number versus the number of expected. Okay, and this expression is weighting things based upon, okay, how connected is one set, how connected is another set, okay, how likely are they supposed to have edges together? That can be bounded in terms of this normalized adjacency matrix, which again, you can simply connect to the normalized Laplacian, and then you have this sort of error correction term. So this is a graduate student conference. I will say that this was one of my early results that I did, was to look at this and sort of say, okay, can you go back the opposite way? So this says, hey, you know, if this eigenvalue is small, then it's fairly random. All right, well, great. Well, in other words, if the eigenvalue is small, your discrepancy is small. So random means low discrepancy here. There's always, of course, a question, how random is my graph? Well, one of the things I did, first big result in my mind, is to say, hey, it turns out the opposite is also true, which says, you know, if your discrepancy is small, so in other words, your edges are very random-like, your eigenvalue has to be small as well, and in a very particular way. So we see, okay, there's this interesting interplay going on in that eigenvalues are telling us sort of how well things can behave like a random thing. So there's this wonderful idea called quasi-random. And this was done, was introduced in the work, Fan Chung, Ron Graham did this. What's quasi-random, right? Well, we kind of have this idea of random. It's like, okay, you go around and you flip a coin, and you make a graph this way. How random is it? You know, how do I know that what I have is random? And so in some sense, you like to have a certification and say, hey, this graph behaves like what a random graph should behave like. In other words, what we would expect a random graph to possess. So even though it turns out you can construct graphs using lots of symmetry and structure, it can still have random-like properties. And that comes by saying, hey, if I can understand the eigenvalues, that's one of our properties for quasi-random, then that can give me saying, hey, this graph behaves randomly and therefore has these additional properties. So mathematicians use this. So for example, Tim Gowers, he likes this idea of quasi-random. And he says, okay, look, I have sort of one of two things. Either I know it's quasi-random, which says, okay, it behaves random-like, I can use the tool, or I can say, okay, it's not quasi-random, which means that there has to be a reason it's not quasi-random, which means there's some structure, and I can use the tool to use that. So this is a really nice way to approach problems. On a side note, I will say, Fan and Ron really love quasi-random, and they actually had an RV for a while when their license plate on the RV was Q-random. So, you know, really embraced that lifestyle there. All right, good. Well, on to another kind of matrix, right? Always more matrices, always more matrices. So the next matrix, well, it's going to be the distance matrix. Now, that one, okay, great. Makes a lot of sense. And we say, all right, we have our graph, and our entries for our graph is the distance between vertices. And we have to add a little asterisk here and say, okay, look, we have to have our graph be connected. Otherwise, hopeless, forget it, forget it. And so here's the POG graph again. And for the POG graph, well, it's not too bad. Entries are 0 on the diagonal because I don't have to go anywhere to get to myself. 1 if you're adjacent, or 2 if you're not adjacent. Of course, you can imagine graphs where very far apart and things get kind of unusual. Well, as always, it doesn't capture everything about a graph. And these are two graphs which are co-spectral for the distance matrix, but they have different structure. Now, the distance matrix is really kind of strange. Now, why do I say that? Well, I would say that from a graph theory perspective, this is a terrible matrix. Why? Well, what should matter in graph theory? It's our neighbors. Our neighbors are the most important thing. It's what we care about. But when we look at the distance matrix, it turns it around and says, no, no, no. The neighbors, in some sense, are the least important. It's those vertices that are far away from you, like those ones way out there. they matter the most. And it just seems wrong. It's the neighbors that should matter. So it's not obvious at all that there's anything interesting to say about the distance matrix. But there is, okay. And so for that, we should jump over for a second and talk about something called the addressing problem for graphs. And the addressing problem says, look, label your vertices with strings, 0, 1, or D. And this D, by the way, from the original paper about addressing, stands for don't care. And so what happens? Well, the distance between any pair of vertices is how often do you differ 0 and 1 in the entry? We don't care about the D's. That's why it's called don't care. So, pick any two vertices. So for instance, say you look at 1, 0, 0, D versus 1, 1, 0, 1. Well, they only differ in 0, 1 once. And then this D1, well, we don't care. So you see there's just exactly one difference. So we're exactly one away. Now, what's good about this addressing? Well, the nice thing is, suppose I want to send information through my network. And I say, okay, I know where I'm at. I know where they're at. So I know my address. I know my target's address. Then what I can do is I can say, okay, I know how far I am away. I'll look at my neighbors and say, who's closer? And then I hand that piece of information to them. And they continue the process. And so this is essentially saying you can most efficiently route information from one place to another. Okay, great. Now, why do we like this? Well, it says, look, all I have to know is myself and my neighbors. So I don't have to store the entire graph to be able to know how to pass information efficiently. So that's why this addressing works really well. Now, how does this connect to the distance matrix? Well, the way you do it is to say, hey, let's look at any single entry. And I can say, if I look at the first entry, you see there's 0 or there are 1s. So I've marked 0 and 1s here. And I can say, well, look, this first entry contributes 1 everywhere where I see a 0 and 1 difference. And so I can think of that as a little matrix where it's a 0, 1 matrix of some sort. It's actually an adjacency matrix of a complete bipartite graph. In fact, that's generally true. And I do it for each entry. So this is the first entry in the labeling, the second entry in the labeling, and again for each one of the vertices, and so forth and so on. You'll notice in the last entry, there's some don't cares. And so, okay, don't cares, you get lots of zeros, but still we say, hey, look, each of these matrices are very nice. They have nice structure. They're adjacency matrices of complete, I'm putting complete in quotes here, bipartite graphs, just because, well, the parts where there are edges, those are complete bipartite graphs. So why does this help? Well, that says, hey, each one of these matrices has one positive and one negative eigenvalue, and the rest are 0. Okay, great. When we add them all together, we get the distance matrix. Okay, that's not so bad. That makes sense, because really we're storing how far apart we are. And now comes the fun fact. Suppose I say, how many positive eigenvalues can I get? Well, the answer is at most the number of pieces over here. So the length of our address bounds the number of positive eigenvalues. Similar, the length of our address bounds the number of negative eigenvalues. Again, this is using the fact that each one has one positive and one negative eigenvalue, and I'm summing these up. So we put those two facts together, and lo and behold, we get the result of Graham and Pollock. It says, look, the length of a valid address is at least as long as however many positive eigenvalues you have, or however many negative eigenvalues you have. Great, beautiful. So there's this nice spectral connection showing up. And so now, all right, well, why is this the Graham-Pollock theorem? Because most people, when they hear Graham-Pollock, think of the corollary. Well, what's that? It says, hey, the edges of Kn cannot be decomposed into fewer than n-1 complete bipartite graphs. Well, how do these two connect? The answer is if you think about your graph, if your original graph is Kn, then this has a really nice distance matrix, namely zeros on the diagonals and ones off the diagonal. And now what you start thinking about is like, okay, great. Well, when you talk about your labeling problem, your addressing problem, that's really one of these complete bipartite graphs is one slot in your address. And now that's where our decomposition comes from. And the other nice thing is to say, look at the spectrum. The spectrum for this, you have n-1 as an eigenvalue, and then a bunch of -1s. And we say, aha, there's n-1 of them. And so we say, since there's n-1 negative eigenvalues, you have to have at least length n-1 for your address. And so that's why we have the Graham-Pollak result. Now, I will say, by non-spectral techniques, Peter Winkler said, hey, this is also, turns out, you never need more than n-1. But that's a non-trivial result. I will also add that Ron Graham once said that this paper, it's not a very long paper, was one of his most fruitful papers. And in the sense that he was able to say, look, a lot of work came out of it, but also, he said, we were able to show people, hey, there's something interesting about the spectral properties of the distance matrix. So it's a beautiful, beautiful result. All right, good. Well, now, question, of course, this often gets asked, and we've been talking about spectral graph theory. We've been talking about the matrices, and you might say, well, is this good for anything? Because that's a question people ask. Now, that's not a good question to ask a mathematician, because our response is, but we love it. And I enjoy working on it, and that's why I study it. So how dare you ask me, is this good for anything? But okay, it's a reasonable question to ask. And so I will say that spectral graph theory is starting to show up more as a tool in results that really you don't look at and say, oh, that's a spectral graph theory kind of result. So let me mention two of them. I'll go through them. I have a few more minutes here. So one of them, Lincoln Liu, he used spectral graph theory to find small Folkman graphs. Now, what's a Folkman graph? Well, it relates to Ramsey theory. So, for instance, you know, if you two-color K6, say red and blue with the edges, what must be true? Well, if you two-color the edges, you either have to have a red triangle or a blue triangle. Okay, great. Well, that's famous. Okay, now you might say, all right, so if I have a K6 and I two-color, boom, I have to have a triangle. But do I need a K6? And the answer is no. You can actually get away with it if you take a graph, namely if you take K3, join the graph C5. So this has 8 vertices. And again, you color red, blue. Then you can show you have to have either a red triangle or a blue triangle. Okay, all right, great. Now that has a K5. All right, can you get away without a K5? And the answer is yes. I think there's a graph on 17 vertices. I don't know it off the top of my head. You can have no K5, red, blue, and lo and behold, everything's good. Now, that graph that I mentioned has a K4. Is it possible to have no K4, two-color, red, blue, and still force a monochromatic triangle? In other words, it's almost as close as we can get, right? So there's no K4. There's lots of triangles. There's tons and tons of triangles. You two-color, and lo and behold, something's monochromatic. And the answer is yes. So this is what Folkman graphs are. So Folkman graphs say, and it doesn't matter, you can have any parameters involved. So it's a generalization of Ramsey theory. Now, why do we want small Folkman graphs? Well, the proof of Folkman was towers and towers. And so terrible bounds, terrible bounds. Joel Spencer came up, said, hey, there's this paper, 300 million points suffice. So, okay, you can do it with 300 million vertices. Then I said, oh, typo correction, 3 billion. All right, 3 billion. Well, Erda shouldn't like that. He said, look, there's got to be something smaller. So he offered prize money. And this one was kind of unusual for him. He said, look, I want something at least as small as 1 million, but the smaller you can make it, the more money you get. So it's like $1 million divided by the number of vertices. That's how much I'll give you. And well, it's hard, right? Because there's many things. But what happened, the hard part isn't making graphs without a K4. The hard part is showing it must have something monochromatic. So that's where Lincoln Luke came in. And look, you can use spectral graph theory to guarantee something is going to be monochromatic. All right, another thing, I can see my time. Almost.
Real quick, Steve, could you clarify what a join of graphs is?
A join of graphs. Oh, okay, sure. I'll draw a picture. So what you do is you take K3. So here's your K3, and then you take your C5, and let's see, hopefully, okay, I can count, good. So a join is you just say, all right, put in all possible edges between those two. That's what a join of a graph is. And so it's very dense in between. This one I'll just mention how Huang proved the sensitivity conjecture. And what is that? Well, that says, look, suppose you take the hypercube, so a high dimensional cube, and if I take half the vertices and take an induced subgraph, well, it's possible I can take just the right ones and have the induced subgraph have no edges. So there is a subgraph. So there's 2 to the n vertices on this graph. There's a subgraph with 2 to the n minus 1 vertices, induced, and degree equals 0. That's not so hard to show. Again, just take like every other one. But the sensitivity conjecture was the following question. What if I say just one more? What happens? Just one. And how bad can it be? What can you say about the degree? And so there was a problem for a long time. And Hao Huang said, look, you have to have something. There has to be a degree of some vertex, not all vertices, but at least one vertex has to have degree at least root n. So that was the sensitivity conjecture. So it says, look, once you have that sort of one more, not only do you have to have something, it has to be a non-trivial of something. Your degree jumps up. It's like Mantel's theorem. Sure, if you have n squared over 4, you can have no triangles, n squared over 4 edges in a graph on n vertices. It's possible to make it no triangles, complete bipartite graph. But you add that one more edge in. You don't just add one triangle, you're actually going to add a bunch of triangles. And so this was a result. And it was all done by spectral graph theory tools, by looking at the eigenvalues. The whole paper takes less than a page and a half. And it's beautiful, beautiful result. All right, so my time, I think, is basically up, but I do want to get back to that distraction. Well, what does it have to do with spectral graph theory? There's 2 products in graph theory that, well, there's many, but there's 2 that are very nice, very simple. The Cartesian product, which says, okay, if I look at the Cartesian product, it says, look, one of the pairs has to be an edge, and the other one has to be the same. That's when I have something stay adjacent. And then you have the tensor product, says, look, both pairs have to be adjacent. So I've drawn the Cartesian product for the 3 cycle with itself, and the tensor product for the 3 cycle with itself. Okay, and now 3 facts. Turns out that for the adjacency matrix, when you look at the Cartesian product, you add the eigenvalues, the 2 smaller matrices. For the tensor product, you multiply. All right, this is looking promising. And then there's this one beautiful fact. It turns out that if you have a cycle on an odd number of vertices, the Cartesian product is the tensor product. So, for example, these 2 graphs, which don't look that similar, are actually the same graph. This is the danger of when you draw pictures. It's hard to convince yourself that things are actually different because you get too stuck with the picture. So, well, how do we use this? Well, so it's great. Just take the adjacency matrix, find the eigenvalues for that odd cycle, and we know them. And lo and behold, this is a set S where the sum of S is equal to the product of S. And it always works. And the example 2 minus 1 minus 1, that's the adjacency matrix of the 3 cycle. So, all right. Well, thank you for coming, and let me know if you have questions.
Yeah, thank you very much, Steve. I suppose those of us on the panel can clap. Everyone's clapping at their house, I'm sure. All right, so we already got another question coming in. Okay, Robbie asks, are there other sets with S plus S equals S times S?
Not that I found. I was interested in it and said, oh, this would be cool if I could find another graph with this. And so I ran through, I think I got through all graphs on 8 vertices, and I was like, it's only the odd cycles. So, so I don't think you're going to find another one based on looking with this fact. Just, it's a wonderful coincidence. And the way it was found, this was actually found by Tracy Hall, who is quasi at BYU. That's well, there's a story behind that. And we were working on a project, and we said, okay, well, there's something interesting about the Cartesian product that's showing up as an example. And then he came back a couple days later and said, we were thinking of it the wrong way. It was actually the tensor product that was interesting, but we were, we don't usually think of this graph in terms of the tensor product. And hey, they're actually the same graph. So.
Okay, next, sorry, next question. We got a lot of questions coming in. This is awesome. The next one I see is, would the eigenvalues from the 3 matrices together determine the graph?
This is a wonderful question. And I've had people ask me this. Some people say, okay, maybe we just haven't found the right matrix yet. Maybe there's like some ultimate matrix out there which captures everything. And if we just had that matrix, life would be good. And the answer is no, there is almost certainly not one of those. There is something called the generalized characteristic polynomial, which actually says, look, I can capture all the major matrices I've talked about. Well, not the distance one, but I can talk about the adjacency, the Laplacian, the normalized Laplacian, sinus Laplacian, and a few others. And we know examples where things are co-spectral for all of them. Now, why should we think that there's no ultimate matrix? And the answer is, if there were such a matrix, that would say I could do the graph isomorphism problem in polynomial time. And it's the graph isomorphism problem is not believed to be polynomial. And so that's why I personally think that there is no ultimate matrix, which is great. It means we get to keep exploring. There's plenty of matrices to look at.
Thank you. And thank you for the question. The next question is, matroid theory also gives useful information from the graph. So is there any direct relation between spectral graph theory and matroid theory?
I have to admit, I'm not well versed in matroid theory, but I do know that there are people who work in both, that they overlap. I do think that there are connections, but I can't give anything really useful in that direction as an answer.
Thank you. Next question is from Vic, who says, have people examined the Smith normal form of the distance matrix of a graph?
I don't know that one off the top of my head. There is a nice survey paper that's been done. So if you look at the survey papers on the distance matrix, I will say that there's lots of other versions of the distance matrix. So people have taken it. There's the distance Laplacian, for example, you can do that. And so for sure, there is some matrix out there where you can find, okay, people have not looked at the Smith normal form. But yeah, I don't know the answer to that one.
Thank you. Okay, there's 2 more questions so far. Can the question of giving addresses in the set 0, 1, d to the n to vertices of a graph be seen as computing something like an isometric embedding of a graph into a cube? Also, maybe you can see these, since that was maybe a lot to hear out loud.
There's basically papers called embedding graphs into squashed cubes and isometric cubes. Yes, there's a whole bunch of literature on that. Yes. I will say that there's a version of the addressing problem for directed graphs. And for that one, like nobody knows what's going on. Like there's not even like good balance. I don't even think the cycle is known. Like, what's the best way to address the directed cycle? And that's because, there's probably not a good, I should add that for the Graham-Pollock theorem, I know most of the results, or most of, I should say, the proofs of the Graham-Pollock theorem heavily rely on linear algebra. And there are proofs of the Graham-Pollock theorem that don't rely on linear algebra, and they're terrible to read. They're just really, really bad. So linear algebra is good. Nothing else. Just remember that linear algebra is good. And so, yeah, there's open problems on the addressing problem still.
Okay. Now your next question from Bishal: are there results where the complete spectrum is looked at and more information is gained?
Well, I mean, I guess the question is, well, what do you mean about information being gained? I mean, certainly there is information in the spectrum, but you should always remember that when you're looking at the spectrum, you are in essence sort of losing information. And so when you think about your matrix that you start off with, that's the number of vertices by the number of vertices. So usually it's n squared, and so you're collapsing down to n, and so you're getting sort of a snapshot of what's happening. So Fan Chung in her book Spectral Graph Theory sort of said, hey, there's sort of an analogy. It says, look, I want to understand something about what's going on where I can't somehow measure it directly, but I do it indirectly through these eigenvalues. And the example is, well, we have all these stars, and we say, look, I know what this star is made out of. Well, how do we know that star is primarily hydrogen? Or how do we know that star is primarily helium? We can't go and collect anything. We can't even go and collect anything from our own star, really. But what we can do is we can look at the spectrum, in this case, the spectrum of light. And that captures information about the behavior. And so we're using that spectrum to infer larger properties. And that's what's happening in spectral graph theory. It says, okay, we can use that spectrum to infer larger properties. I will add, it is widely believed that if I have the spectrum for a graph, very likely, with high probability, that's the only graph with that spectrum. In other words, most graphs have a unique spectrum. There are some people who take a contrary opinion just because, well, it's good to have somebody play the devil's advocate, be on the opposite side. So there is a lot of information that's stored in spectrums. Another thing I'll add, and this maybe is a bit more philosophical, is I don't think that we actually have learned to use the spectrum as well as we could. If you look at most of the results in spectral graph theory, they say, okay, look at the largest eigenvalue or the second largest eigenvalue. I think I've seen one result that said, look at the third largest eigenvalue. There's not a result that says, well, if you look at the 17th largest eigenvalue, then you can really gain information. It's like, no, nobody looked that far down. And so we don't really understand enough. And the reason that we don't really understand things, and there's a weakness, the farther down we go, is because of sort of the sensitivity of various conditions in the graph. And that is to say, a lot of graph parameters are so sensitive, the addition or deletion of a single edge can change it. So like, okay, I have a bipartite graph. I could add an edge and have it not be bipartite. All right, well, where are your sensitive eigenvalues? And the answer is, the sensitive eigenvalues are almost always at the end, because the interlacing says you can only move your eigenvalues around in between where your current eigenvalues are. So if I'm sort of deep down, I really can't wiggle much. And that's why I suspect we don't really see a lot of results using the 17th largest eigenvalue. We almost always see results at the end. Yet somehow those eigenvalues in the middle, they have information. And how do we extract that?
Thank you. And then so there's two questions left, and they're very, very similar. So I'm just going to ask them together. Is there any way to define spectrum of hypergraphs? And then if so, how developed is that theory?
There's lots of ways to define spectrum of hypergraphs. And so I mentioned Lincoln Liu, And so he's at South Carolina, and Josh Cooper is at South Carolina. And they both were at a conference, and they gave a talk, both of them, about the spectrum of hypergraphs, and they had completely different definitions. They, by the way, they also had the same advisor. Van Chung was their advisor. And I remember Josh Cooper saying, even though, we have the same advisor, or we work at the same school, we didn't realize we were both working on the spectrum of hypergraphs until just a few months ago. And so the thing is, the reason I say this, there's lots of different ways to do it. Almost every way doesn't seem right that we've looked at. And so I do remember Josh Cooper's talk on it once, and he says, okay, here's this procedure, and we have all these nice things. If your spectrum does this, you have this property. And they said, well, we were able to compute the spectrum for a graph on four vertices and 6 edges, something on that order. And it took 2 weeks. It was just like, okay, forget it. Hopeless. So yeah, their hypergraphs are definitely a big direction people are trying to go in, and they haven't nailed it down. There are many different definitions out there. There's not a universally agreed on, like, this is the right way yet. So maybe you can find it. You can be the one.
Okay, thank you. I think we're all leaving this talk with a lot of things we can look at after this. There are no more questions, and we are a little past 12:30, so this is a good time to wrap up. Thank you again, Steve, for the fabulous talk.